Good morning, I'm Michele Messori, and I'm here to present my work on security and performance issues in a large-scale complex system. My tutor is Professor Michele Colajanni. At the base of my research activity, there are large-scale complex systems. They are characterized by a high number of locally or geographically distributed nodes and connected by heterogeneous networks. In this scenario, centralized solution do not work very well enough, so I focused my research on distributed and cooperative solutions. Starting with security, I studied and designed a new architecture that permits to every node to communicate with each other nodes. And we can divide every node into 3 different layers. At the base, we have the analyzer that are able to detect many kinds of attacks. For example, intrusion detection system, log analyzer, honeypot. All the alerts are sent to the next layer, that is the local aggregation layer, where we have the alert collector that aggregate and normalize the data and then store that in the local alert database. On the top layer, we have the collaboration module that is able to get the stored data and send messages over the network. At the same time, it is able to receive and process messages from the other nodes. For example, if we have a node under attack, it will generate different messages, for example, IP address of the attacker, the kind of attack, or for example, the binary code of a received malware. We have multiple copies for every message. In this way, if a node fails or disconnects from the network, we can have a replication message, backup data. If one node receives the message, he can analyze it. For example, he can analyze the malware binary code and extrapolate useful information to defend every single node from this kind of attack. Then he sends a report with this information to all the nodes, and we can consider that all the nodes are protected or at least informed. In the second scenario, talking about performance, I'm focusing on cloud infrastructures where we have several nodes, and for every host we have a lot of virtual machines. Thanks to the progress in technology, we are now able to migrate every single virtual machine from one host to another without stop them. This is called live migration. There are a lot of algorithms to study when to migrate a machine, how to migrate, where to move the machine. We focused on reduce the number of live migration, then to reduce the bandwidth consumption, and to obtain a more robust system. For example, consider this graph where we have the CPU load of one host. Threshold-based algorithms will fail when we have a load over the threshold. They can't manage this load. Existing solution can try to detect the trend of the virtual machine of the load, but we have studied an improved algorithm, and we are able to detect not only the spikes, but also the real change of state. In this case, we have only 3 migration against the 5 of the existing solution. So we have less migration and a more robust system. These are the 2 papers that I've published. Thank you for attention. Any question?